Right, I'm going to try and use this for the first time. Okay, so today I'm going to be talking about reducing energy costs by establishing the relationships between energy usage and production variables. That's a bit of a mouthful, but basically it's a way of linking production usage, energy usage to your production processes. So the company I work for is called Structured Productivity Solutions, or SPS for short, which is a lot nicer way of saying it, really. We produce a product which is called Factory Management System, and basically it monitors and records real-time production processes and parameters. And it also processes this data into near-live online views which are available on the data entry touchscreen, and also on a website so it can be viewed remotely. We also produce regular printed reports, and that's as part of our consultancy package where you can give more focused bias towards certain aspects of your production. So, how did we become interested in energy? Well, one of our customers asked us, can you record energy consumption using the factory management system? And luckily, we could. Because we can record data from any number of external sources and synchronize it to the production data that we're recording in real time. So, let me show you some examples here. We've gathered some data. What we're going to do is we have a pulse which comes in from the energy source, which we record as a count pulse. So we need to convert that into a set of units that we can use that makes sense. Yeah? In this particular case, we are going way ahead. What's going on? Yeah, so we've got to convert it into useful units. In this particular case, we're using kilowatt hours per ton. So we're focusing on bricks here. Yeah, so we're using kilowatt hours per ton. So, let's have a look at an example here. The columns here, we can see the monthly breakdown, and this is the average number of kilowatt hours per ton to produce all products over that year. As you can see, the variation is about 15%, depending on the product that's being used. So there's a variation within it, yeah? So you can look at that a little bit closer and break it down on a weekly basis. And this time, we see there's a 39% variation, which is a bit odd, so we look even closer. We can see on a daily basis, 80% variation. So you can see that, okay, on the daily basis, there's an 80% variation, but as time goes by, it averages out to a smaller number. But you can see that if you come down to the smallest level, there's a huge variation. So, what's going on here? Well, FMS allows us to look at this data further to do energy consumption versus real-time production events. So we can align energy consumption figures against a range of production parameters, including the time of day, date, shift, down reason, product, plant item, etc. So, looking at the previous data, with reference to product, here we can see the first column shows the different products. The second column is obviously 2012 because we're looking over the entire year. And then we can see that there are varying amounts of energy required per unit of product, depending on the product that's being made. And it is varying. So if we look at wine groves in particular and drill down on that, we can see that even for a given product, the actual runs that we have still produce a variation. That's the run variation. So it's like even with the same product, there's still a difference. So what can we conclude from this? Well, energy consumption per unit varies according to product. So when we do our analysis, we have to bear in mind that it does vary according to product. We need to make sure that we look at it from the same angle, i.e. we put a product focus on all the data that we're looking at. So for example, looking at the Wayne Groves example again, we can compare the two shifts, but we have to compare it to the same product to get a true reflection. And here you can see that there's a different energy requirement on a shift basis, making the same product. So, why are they different? But one possible reason for the difference in energy consumption is that the operators run the plant in different ways. Next few slides, we'll see how different operators influence the production process. Now, we're going to look at an example here. It's not a brick manufacturing company, but it shows the principle. This is a data sample taken over a 14-day period. So here, we can see over here, on this column, we've got the total number of minutes that are lost due to downtime, which is 2,800 minutes over the 14-day period. And that's the total downtime for all shifts. So if we break it down, we can break that down on a per shift basis. So we can see that in this case, total downtime can be broken down as well. Yes, you can see that shift B is most of the downtime. We can try and isolate where that downtime is being incurred. So we break down the downtime reasons, and we can break it into its constituent parts, i.e. electrical, mechanical, operations. You can see that by far the bulk of the downtime is associated with shift B during operations. Now we can break down operations even further into its subcategories. And here we can see the difference between shift B and shift D in the way they operate the plant and the total number of minutes that are lost due to downtime. You can see that shift B loses a lot of energy during the production of cobble and also in mill delays. Now shift D, on the other hand, does things in a very different way. They are far more proactive in setting up the plant to produce the product, and they consequently lose less downtime, and in this case downtime equates to energy loss. So you can see from the previous example that energy is being wasted during stoppages, and the D shift has considerably more stoppages than the others. So we go back to our brick manufacturing example. The likely reason for energy consumption variation is downtime. So let's look at another example on a dehacker. But first, do a couple of explanation terms. Direct energy. That is energy that can be directly attributed to the manufacture of that product. Indirect energy is energy that is used in the manufacture of the product, but not directly. So it could be something like, for example, downtime, where energy is being used even though the plant is not running. We have actually produced a white paper on this, which you can see. If you go to the website, which is associated with my email address at the end, then you can find some information on that in there. So, coming back to, coming to the dehacker example, we can see here that the total energy usage, of that total energy usage, 13% of it is consumed during downtime, i.e. when we're not producing product, i.e. waste, potentially. So we take that 157,000, break it into its constituent parts. You can see that by far and away the majority is due to operations. You can drill that down further. Now in the project, you just click on the category and it will drill down to the level below it. It's a very simple thing to use. You can break it down, and again, you can see the bulk of it is to do with slow running. So you break that down. And of the 34,500 minutes associated with the downtime due to slow running, you can see, okay, you can see the breakdown, but we can look at this figure and say, well, is it influenced by shift? Is there one shift doing something different over another? And here, we can break it down. We can see the two shifts. Yeah, we've got the down reasons due to slow running in this column, and then we've got two shifts in these columns. And you can see there's more than 4 times the amount of energy used by B shift than it is by A shift. So, it's all well and good finding out the root cause of the problem, but we need to close that loop. We can identify where the energy is being lost, but to be effective, we need to make sure that we make operational changes to get over those lost energy as a result of the downtime, for example. This data needs to be understood by those who directly influence the outcome. So it's going to be in a form that's easily assimilated by the operator. So this is an example of a live view that's available on the touchscreen, actually on the production line. And from this, you can interact with it, and for example, you can drill down on the various components to see where any underlying causes lie. So this is, we're looking here at the energy lost during downtime, and in particular we're looking at operations. So we can drill down operations, again, like we did before, and we can see, if we look at weighting, which is the blue column here, we can break that down into its constituent parts again. And this is a very interesting slide. You can see there the drop. Yeah, you can see with 29, 30, 31, 32, they're quite large amounts of lost energy. And then suddenly, with 33 and 34, the energy lost during waiting for kiln cars suddenly drops. Yeah? And why is that? Well, as you probably just saw 2 seconds ago, there was feedback saying, when you're waiting for the kiln cars, switch off the plant. Now, obviously, there's certain things you can't switch off, but like the conveyor belts and stuff, you can switch all of them off, and you save energy as a direct consequence. And that shows you the direct consequence, or the direct effect that it has on energy loss. So that's feeding back the information you found, and it has a direct effect on the outcome. So today we've only looked at electrical energy, but this would apply to anything. It could be a gas consumption meter. As long as it has a pulse output, we can record it. And also, of course, things like CO2 emissions. We can monitor that as a directly with the production data, so we can align it and look into the causes of it, and if there's any way we can reduce those emissions.